Okay, so I hope everybody is doing well. Let's see if this class goes well. We'll probably have to change some things as the semester goes on, but let's see if this is a good solution for now. So what we've been seeing in class so far, we've been looking at probability triples. So probability triples, which are given by omega, f, and p, where omega is the sample space, f is the set of measurable events, and p is the probability function. Okay, so what we're going to be looking at now is random variables. And in Portuguese, this is called variables aleatórias. Variáveis. So what is the idea here? So the idea is that instead of looking exactly at what W in omega we are getting, we care about a quantity associated to what a specific point in our sample space we drawn out. Okay, so instead of looking at the specific omega in omega, we are only interested in a quantity associated with it. Okay, so what's the example? So the idea is that we're going to consider x, which is a random variable, as a function that is going to go from our sample space onto R. Okay? So let's look at an example of this. So let's say that we randomly, we randomly draw a person from a city. Okay? So our omega would be all of the people in the city. But the only thing that we actually care about is their height. Okay? So we care about how tall they are. Okay? So we would have x, which is going from omega to R, or actually, instead of R, we would actually be just getting a positive R plus. So we're going to have x that is going from the people of the city into R plus, which is giving us their height, which x of omega is equal the height equal to the height of person omega. Okay, so that would be one example. I'm not saying what the probability distribution would be, but let's say that we are uniformly sampling over all the people. Okay, so what's next? As another example, we could consider rolling two dices. Okay, so in this case, we would have the sample space to be 1, 2, 3, 4, 5, and 6 squared. Okay, so we are rolling two dice so we can get 1 through 6 through each of the dices. And we care about the random variable which is given of the sum of the two dices, okay? So we are going to consider a function which is going from omega to r. Again, this is a random variable. X is our usual notation. And then what we want is that x of I comma j is equal to I plus j, okay? So this belongs to the sample space, and this belongs to R. Okay, what other examples can we have? So for instance, the example that we've been treating a few times is like, what if we flip a coin 10 times? So what we would have is that our sample space is going to be heads and tails 10 times. Okay? So, but usually we don't actually care exactly if we have gotten the heads in the first 3 draws and then we got tails afterwards, or these kind of things. Like, we don't quite care about the order, but we only care about the quantity of heads. Okay? So then we would have x, which is going from omega to r, which basically is just telling you the quantity of heads for some specific omega in r, okay? So let's say that omega is equal to heads, 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 and then tails, 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 tails. Okay? So this is a specific point in omega, and then we would have x of omega is equal to 3. Okay, so all of these examples of random variables would be discrete, but then we could also have random variables which are continuous. So for instance, we could have like the example of a random point in the unit disk. Okay, so we have the unit disk. Okay, and we pick a point at random in this unit disk, and then perhaps we are only caring about what is the distance between 0 and the random point that we're getting. Okay, so, and we care about the distance to the origin. So, in a sense, okay, the way you could think of this is that this is like you're really bad at throwing darts. Okay, so you throw darts to this target, and you like are so bad that the only thing that you are able to is hit the target, but you cannot put it in a specific place. So randomly your dart will hit anywhere in the unit disk, and then you are getting points as close as you get to the origin. Okay, so omega would be equals to the x comma y, such that x squared plus y squared is less or equal than 1, and x of x y would be equal to the square root of x squared plus y squared. Okay, and x again is a function that goes from omega to r. Okay, so now what's next? So basically we have introduced what a random variable is by a few examples, but the point is that we are going to ask some relationship of the random variable of the definition of our function with respect to our probability triple. Okay, so morally x has to be measurable. Okay, So the way that we assign values in omega has to be related to the set of measurable events and, of course, the probability function. Okay, so the idea is that the requirement for a function x from omega to r to be a random variable is that it is measurable. Okay, so what do I mean by measurable? Okay, so this is a concept that usually you see later on in like real variables or something like this. So the idea is that the pre-image, and so here it would be measurable, and in this case it would be what's called considered Borel measurable. So the pre-image of open sets needs to be a measurable event. Okay, so let's write this down in a definition. A function x that goes from omega to r is called a random variable if for any a comma b in R we have the inverse of the set of the open set AB is a measurable event in F. Okay, so this is for any AB and A less than B. Okay, so every open set has a pre-image, which is something we can assign a probability of. Okay, so just a reminder, we have the P, the probability function, goes from F to 0, 1. So we can always, with this definition, we can always assign the probability that the random variable lands in a particular open set. Okay? All right. All right, so what is an observation? As we usually do in this class, I mean, this type of definition and this type of things make more sense if you're looking at continuous probability models. But if you're looking at discrete probability models, this becomes a little easier. So let's do a remark. If omega is finite and f is equal to parts of omega, then any function x from omega to r is a random variable. Okay, so in general, for finite probability models, this is not going to make much of a difference. But for continuous probability models, there will be some functions that will go from your sample space to R that you will not be able to accurately say if they belong to a certain, like assign probability for them to belong in a certain open set. Okay. Okay, so associated with a random variable, there is a tool, or there is the distribution function, which is fairly powerful to get some properties of random variables. Okay, so we say, okay, so let's see, definition. Okay, given a random variable x, its distribution, function is given by f that goes from R to 0, 1, which is defined by f of x is equal to the probability that your random variable is less or equal than x. Okay, so what I want to say here. So the point, so one to relate it to the definition of random variable, we should be a bit careful here, because I mean, here I've talked about being able to give a probability associated with any open set. Okay, and so this is a, b, and r, and then you can also take a to be equal to minus infinity and b to be equal to plus infinity. Okay, so these are also valid choices. So one thing that one could ask is, here I'm taking a closed set. Okay, so here this set is x is in minus infinity, comma x closed. So a question would be, if we are able to assign a probability in an open set, can we actually assign it in a closed set? And the remark should be that if you can assign a probability to the open sets, then you will be able to assign the probability of the closed sets by the complements. Okay, so closed sets, so remark, closed sets are the complement of open sets, hence using the sigma algebra property of f, we can assign a value to p of x less or equal than x. Okay, so morally what I'm saying is x less or equal than x is equal to the complement of x bigger than x. Okay, and this is the complement. So this without the complement is in F. By using the sigma algebra property, the complement is also in F. So this guy is in F. Okay, so what is the idea of making this definition? The point is that the distribution function is a way to encode your random variable. Okay, so given a random variable, f basically determines it uniquely. So in terms of notation, if you want to make the relationship between x and f, you can write f of x, depending what is the name of your random variable. If it's x, y, then you just change the subscript here. Okay, so let's look at what is the random variable associated, what is the distribution function associated with a certain random variable. So for instance, let's look at some easy examples. So example, let's say we consider flipping 2 coins. So this is the example in which we would have sort of heads, tails, squared. And we consider x to be the number of heads. So here it would be an example that we have a discrete sample space and f is equal to parts of omega. So any function that we take x that is going from omega to r will be immediately a random variable. Okay, so what is the distribution function in this case? So f of x, okay, just to put the notation, this would be the distribution function associated with a random variable x, is going to be the probability that x is less or equal than a specific variable. Okay, so this is a discrete variable, so the point is that it will depend sort of only on discrete values of x. Okay, so this would be equal to, let's see how we write it. It would be equal to 0 if x is less than 0. Okay, so what is the probability that you have less than 0 heads? Okay, so 0 heads is the lower bound, so you cannot, the probability of this will be 0. So then the next change happens at 0 less or equal than x less than 1. So what is the probability that you get between 0 and 1 heads? So basically, what is the probability that you get 0 heads? This is going to be 1/4, because this is the probability of getting exactly 2 tails. Then what is the probability that you get between 1 head and 2 heads? So basically, this is exactly what is the probability that you get exactly 1 head, and this would be equal to 3/4. Sorry, because here this would be the probability of getting 1 head or getting 0 heads. So the probability of getting 1 head is 1/2, and the probability of getting 0 heads is 1/4. So summing 1/2 plus 1/4, we get 3/4. And then finally, what is the probability that you get less than 2 heads? The probability that you get less than 2 heads will be 1, because you are flipping the coin only 2 times, so you can only get at most 2 heads. Okay, so this would be, if we try to plot this function, here we have x in R, and here we have f of x. So for x less than 0, we get this is 0. For x equals to 0, this function jumps to, let's say, 1/4, and here the value is the value of 0 is up there, and then we have until 1. Then we have another break at 2. So from 0 to 1, you have the value 1/4. Then here you have 1/2, and here you have 3/4. Then you would have from 1 to 2, you get the value 3/4, and then from 2 onwards you would get the value 1. Okay? Okay, so this is an example of given a random variable, how you can actually find its distribution. So morally, you have to, in the case of a discrete random variable, you have to look at which are the points in which there is a jump of the probability, and then basically you get a piecewise constant probability density. So one of the things is, as you note, I have marked this side because this, as we will show, the probability density function will be right continuous. Okay, so the value from the right is going to be the value at the endpoint. Okay, so you have a discontinuity, but if you look at it from the right hand side, this guy is continuous. Okay, so what other example we can do? So, okay, so this is a discrete variable in which we have jumps, and then we can have an example of a continuous variable. So another example would be usually when we take a random point in 0, 1. Okay, so this is omega. This is a continuous probability space. So this is a random point in 0, 1 with uniform probability. Okay, and we would have, so let's say that we care about the simplest random variable in this case. We would just have, so if we have omega, little omega in big omega, then we would care the function x from omega to r, which is just given by x of omega equals to omega, okay, which is a number in 0, 1. So for this random variable, we would get that fx of x is what is the probability that I draw a number that is less or equal than x. Okay, so again, we will have a couple of different cases. So if x is less than 0, you clearly get equals to 0. If x is between 0 and 1, we would get x, which is the probability of being in a certain interval, will be just the size of the interval, and the size of the interval in this case is x. And then the probability that x is less or equal than 1, so here we probably want to put the open set, 1 less or equal than x, you would get 1. Okay, so the function, the graph associated to this function would be something that is 0, and then you have a straight line and get something like that. Okay, so this is a pretty simple example, but now this gives you an idea that there is different types of random variables. So we'll have random variables that look like this, in which there is a jump at discrete points, and then there are other random variables associated with continuum spaces in which we would have something which is something without jumps. It might have kinks, but it doesn't have jumps. Okay, so the behavior of these two random variables will be slightly different. Okay, so now let's look at another sort of trivial example of a trivial example which is used a few times for mathematical purposes. We will look at the constant random variable. Okay, and here we would have x that is going from omega to r. Okay, so this will be a function that for every point in your sample space, you will be a specific constant c. Okay, so for every point in the random space, you are given a constant c, which is independent of omega. Okay, so as I said, this is more of a mathematical trick in some sense. So this will always be a random variable. Okay, so you can have an exercise show x is always a random variable, and this is independent of what the set f is going to be, because morally either c is in your set, which means that the preimage will be the whole of omega, or c is not in your set, hence the preimage will be empty. And f, the set of events, will always contain the full set and the empty set. Okay, for this random variable, we would have that f of x, again, this is the distribution function associated to x, would be the probability that x is less or equal than x. And here we have two choices. Either x is larger than c, or x is less than c. Okay? So if x is less than c, then the probability that x draws that value is going to be 0. But if x is bigger or equal than c is less or equal than x, then we will get that the probability is 1. Okay, and in this case, we would get that the graph of this guy looks something like this. So here you have the value c, it's 0 all the way here. Here we have 1, and here we have a right continuous function that takes the value 1 for every value bigger than c. Okay, so we gave a couple of examples of this guy. Let's now look at a couple of properties. All right, so what are the properties that we've been talking about? So the properties that we've been talking about is that this guy is right continuous. Okay, so whenever you approximate the value from the right, you would actually get continuity. The other thing that all of these guys have in common is that if you look at them, they're all increasing. Okay, so this guy is always increasing, this guy is always increasing, this is always increasing. And the third property that we are going to look at is if you take the limit when x is going to plus infinity, then you would expect that the distribution function is going to 1. Okay, so always the distribution function is between 0 and 1. But when we take the limit as x goes to plus infinity, you get 1. And when you take the limit when x goes to minus infinity, you get to 0. Okay, so let's do a proposition. Let x be a random variable and f of x its associated distribution function. Then f satisfies the following properties. Okay? 1. F is non-decreasing. Okay, so that is to say, for every x less or equal than y, we have f of x less or equal than f of y. Okay, and now the other property too is that f is right continuous. So we have that if xn, that is to say, if xn converges to x plus, so this is from the right hand side, so basically if we have x here, we have a sequence xn that is converging from the right, okay, so this is xn. Then the limit when n goes to infinity of f of xn is equal to f of x. Okay, so yeah, so sometimes the notation for this in analysis is the limit when when y goes to x plus of x of f of y is f of x. Okay, one of the things is that because f is non-decreasing, this sequence is also monotonic. Okay, as you approximate the value of f at x from the right, the value will be decreasing. Okay, and the third property that we were mentioning is that the limit when x goes to minus infinity of f of x is equal to 0, and the limit when x goes to plus infinity of f of x is equal to 1. Okay, so let's look at the proof. Let's look at the proof of this. Let's look at the proof of this. Okay, so what is the first property? So monotonicity, or f is non-decreasing. Okay, so what is the idea? So the event x less or equal than x is contained in the event x less or equal than y for every x less or equal than y. But then, as we have seen before, this implies that f of x at x, which is the probability of x less or equal than x, will be less or equal than the probability of x less or equal than y, which is equal to f of y. Okay? So this is a bit straightforward what we're trying to do. So what is the second property? The second property we care about is that f is right continuous. Okay, so here for this second part, we are going to be using, we are going to use the continuity of probability, which is what I called before Borel-Cantelli. So we consider E of En, which is the event that x is less or equal than xn. So if we have that xn is a decreasing sequence, then, so it's a decreasing sequence. What does it mean? Xn plus 1 is less or equal than xn. This implies that En plus 1, which is the set of x less or equal than xn plus 1, is contained in the set En. Okay? And what follows? If xn converges to x plus, then the intersection from n equals to 1 up to infinity of En is going to be the set E, which is equal to x less or equal than capital X is less or equal than the value x. So morally, graphically, what we are doing is the following. So we have the real line, and here we have the value x, and here we have x1, x2, x3, and so on. Okay? So we consider the set, the closed set, which is going from x1 towards the left. Then we consider this smaller set here, and so on. But if we take the intersection of all of these sets, the intersection of all of these sets will eventually just be the one less or equal than x. Okay? All right, so let's show that. So, okay, let's show that the intersection of n equals to 1 up to infinity of E of n is equal to x less or equal than x. Okay? So, the point that we're going to notice is the following. So, a point in your sample space W is going to be in E if and only if x of W is less or equal than x. But a number x of W is less or equal than x if and only if x of W is less or equal than xn for every n in n. Okay? So you're less or equal than x if and only if you're less or equal than the sequence for every point in the sequence. Okay? But this is the same that x is in En for every n, which is equivalent to saying that x is in the intersection from n equals to 1 up to infinity of En. Okay, so what does this mean? Then we can use the theorem, by the continuity of probability. So by the continuity of probability, what we have is that the probability of En, so what we have is that the probability of E is going to be the limit when n goes to infinity of the probability of En, which is equal to fx of xn, and the probability of E is fx of x. Okay, and this finishes the proof of the second property. Now, for the third property, so morally that you're going to, if you take x to plus infinity or you take x to minus infinity, so the idea is that you do the same type of argument using that the union, so the union of x less or equal, let's say that n with n equals to 1 up to infinity is going to be equal to omega, and similarly the intersection with n equals to 1 up to infinity of capital X less or equal than minus n is going to be the empty set. Okay, so this is a increasing sequence that is going to the full set omega. So then the probability of this guy is going to be equal to the probability of the omega, which would be equal to 1. And if you go to the left, you would get that the probability of this guy will be, the limit of the probability of this guy will be the empty set, which is equal to 0. Okay. All right, so to finish up, I guess I will just mention something for you to know further away. So this is something for you to know. So in general, there is what I said, that the density function characterizes the random variable. We can actually have the following proposition. Let f from R to 0, 1 satisfy the properties from the previous proposition. Then there exists a probability triple omega f p and a random variable x going from omega to R, such that f is the distribution function associated with x. Okay, so such that f is equal to f of x morally. Yeah, so morally, how can we do something like this? So the point is that we can, okay, so the proof of this, I'm not going to do it, but the proof of this is morally, let's say that we have, so we have the properties from the previous guy. So we need f to be non-decreasing, right continuous, and with these two properties, which is between 0 and 1. So then you would have something, a function that looks something like this. It could have a jump at some point. It goes up. It could be flat. And then it goes up. And then in the limit, it goes to 1. So morally, what you would do is try to associate probability triple omega fp such that omega is given by the 0, 1. F will be given by all the pre-images of the open sets. So F is the smallest sigma algebra defined by the pre-images of all the open sets of f of x. Okay, so basically you take F inverse of 0a for every a with the closed set 0a for every a in 0, 1. And then the probability density, the probability function p is completely related to f. Okay, so the value given to these functions is given to the value of that guy. Okay, so you have to be a bit careful of how you do it, but the idea is that just using this, the three properties that we have given before will assure that you can actually make p a probability function. Okay, so it's something that is additive. So the property that we need to check is that p of a union b is equal to p of a plus p of b whenever if a intersection b is equal to the empty set. Okay, so the fact that we have this right continuity is what will allow us to do stuff like this. Okay, so I'll stop here for this part of the class, and then later we'll start talking about continuum and discrete probability functions. Okay, thanks.